Hi, everyone. Today we're going to discuss the dot product between two-dimensional vectors, okay? And if you noticed before, we talked about addition, subtraction, multiplication, division by scalars, but we never multiplied one vector by another. Well, that's essentially what the dot product is doing. And in order to do that, when you're talking in Cartesian coordinates, if you were going to take the dot product between v and n, two vectors, v and n, you would take v's x component, multiply it by n x component, and then you would add v's y component plus n's y component, and that would become the dot product. You'll notice that the dot product is a scalar value. It is not another vector. And if v and n were the same vector, we'd be squaring x and squaring y and adding it. Well, here, when you multiply two vectors, you're doing it with two different vectors. So you got v's x times n's x plus by's times my. There's no square root or anything. It's just returning you a squared value, okay? And that's used for a lot of reasons. And one of the reasons down here would be, let's say you wanted to compare the direction or the angle of two vectors to see if they're pointing in the same direction. It's not going to, this formula, of course, isn't going to give you the angle between them. But if you have one vector here and another vector here, and you did the dot product between the two, if the dot product's result is positive, that means both of those vectors are pointing within this range. They're both pointing to the same side. If the result is negative, that means that one of the two vectors is pointing in the opposite direction of the other. If the result is zero, that means either that means it's perpendicular or orthogonal. So in other words, these are at a 90-degree angle to each other if the result is zero. And of course, it could be zero twice, once on the left if it's clockwise and once counterclockwise. Another thing that I want to mention about that again up here, the tails do not have to be aligned when you're doing a dot product. In other words, you can see I have the tail of a vector here and the tail of a vector here. I can still do the dot product. The result is zero. They're still perpendicular, just like when their tails are aligned. The dot product zero. Now these ones are facing in opposite directions, but also look here. The tail of this vector is way over here, and then the tail of this one's over here. So they're not aligned, and the dot product is still valid. You don't really need to pay attention to what this number is, but just note that it's negative because they're pointing away from each other. Same thing down here. Both of them are sharing the same tail location, but it doesn't matter. As I told you in an earlier video, you could basically separate these two vectors and it doesn't change them. They don't need to be at the origin. But you got to remember that their origin is always assumed to be zero. But all the vector is a length or a magnitude and a direction. It doesn't matter where it is on the graph. Okay. And the same thing here. A dot product is positive because both of these are pointing in the same direction. And the same thing up here. And they're not sharing the same, tail location. So I just wanted to make sure that you knew that. But and also it's commutative. You can take the dot product of A dot B is the same thing as the dot product of B dot A. But there are some caveats that you got to pay attention when we discuss these two formulas, which I'm coming up to next. The dot product, besides being used to compare directions, we could use it in another formula to calculate what they call a vector projection. And a vector projection can be used for lighting calculations. Shaders use it very frequently, reflections, and a whole bunch more. But one thing you got to know is that when you're doing a projection, that is a case where both of these need to be pointing in the same direction. You can't have them pointing in opposite directions. They don't need to be tail aligned. They can be apart, but they both need to be pointing in the same direction. Like you could not do a vector projection with these and have make any sense. They should be pointing in the same direction. So you can think of that as the tails are on top of each other and looking at this here. In other words, both vectors have to be on this side or on this side. They can't be perpendicular, of course, because there would be no shadow. All right. So basically, what the dot product formula, which is right here, is going to calculate is this vector down here, P. And if you look at these numbers I have here, this is just an example to give you an idea that you could work through if we were projecting n on the v. And I'm telling you what, first you got to take the dot product of n dot v, and the result of that I have for this example is 1130. And then we're going to take v dot b, which is over here. Okay, the result of that is 19,600. So you can see we're dividing those dot products. If we divide them here, the result of that is 0.58. This formula, the projection, is equal to n dot v divided by v dot b times v. The result of this times v. Now, if v, this is where I said the order would matter. If v, the vector that you're projecting onto, okay, if that is a unit vector, in other words, it has a length of 1 or a magnitude of 1, we could remove the division and the dot product because, 1 dot 1 is 1, and any number divided by 1 is equal to itself. So we can eliminate the division and eliminate this dot product, and now your formula simplifies. So the projection equals n dot v, and then the result of that times the v. All right. Now, again, that's useful for calculating shadows. Imagine that you have this vector and it's a unit vector, and then you have another vector that's up here, and above it there's a light source, and this vector is casting a shadow along the length of this vector. All right, and you want to know how long is that shadow? How long, or how far along the length of this vector is that shadow? Well, you would use this formula here to calculate that. And even though I drew this parallel to the ground, this can be at any angle. In other words, I could take this vector here and have another vector over here and project that vector onto this vector. Okay? And that would still work. It doesn't matter. We could take both of these and flip them all the way so that they're both on this side. It will still work. All right. It doesn't need to be coming straight out. Okay. That's all you need to remember about that. Now, another formula we have here, and you'll like this one even more if you're a game programmer. Let's say you wanted to have a ball collide with a wall, and then you want it to bounce off realistically. So this vector n is coming in, and it's going to hit the wall, and then how would we figure out what this vector is? What is our bounce angle? Well, to do that, we would use the vector reflection formula. Now, if you look at this formula closely, this part where it's n dot v divided by v dot b times v, that is this formula, the projection formula. So basically, that's taking the projection formula and doubling the projection vector and then subtracting the value of all that from the incoming vector. All right. And that would give you a reflection vector. There's one important thing that you need to know about this formula, though. If you look at this vector, you'll see that they are not pointing in the same direction. And as I told you before, they have to be pointing in the same direction. So what you would do in this case, if you were calculating a bounce angle, you would have to invert this vector so that it's pointing this way. It's starting here and pointing that way, just like we have here. It's pointing in the same direction because this won't work. The dot product, it'll mess it up, right? So if you flip this and then you run this formula on it, you'll end up getting the reflection vector. Now, obviously, if this vertical line, we knew it was perfectly vertical, we wouldn't need to do this formula because all we would need to do is take our x-axis and negate it, okay? Flip it, because the x is just going to be going in the opposite x direction. The y value is still going to stay the same. So you could cheat. You don't need to do all this stuff. That's if it's vertical. And of course, if it's horizontal, then you would do the same thing with the y component. You'd flip the y component and leave the x component alone, and it'll calculate a perfect reflection angle. But what if this surface was at 45 degrees or 50 degrees or 130 degrees or any arbitrary amount of degrees anywhere around the circle? Then you can't just subtract from one of the components. That's where this formula would come into play. And that's very useful. In fact, I'm going to do a video about that, and I'm going to show you an example in GameMaker where I actually do this, and it's interactive, and you can see the results of this formula in action. So look forward to that in the next video. And if you like this video, please subscribe, please click like, and please pass it around. And thank you for watching, and I hope you have a great day. Peace.